Professor,
Yeah.
I have a quick question regarding the homework.
Okay.
For the ones that are the homeworks that are due on Wednesday, would it be possible at all to get like an extra day or two to work on them? Just because I'm finding myself struggling to always finish the ones that are just due Wednesday because I'm taking multiple classes and working.
Okay.
Would that be possible at all?
Let me take a look. 1 second. Okay. Excuse me. Due Wednesday, 14.5 and 14.6, right?
Yes.
So when do you want them due?
Even if it's just an extra day, it's just when exams and stuff come up for a bunch of other classes, it just gets kind of overwhelming for the 2 days.
Okay.
Thank you.
Yeah, I'll edit this. Well, this is a weekend where, no, what's going on here? Okay, I think that should be good. Wednesday. I think there's something going on. This is due Monday, that's fine. And then we have our exam. Oh yeah, sounds good. Okay, so if there's two in a week, it's due on Thursday now.
All right, thank you.
Yeah, sure. Sounds good.
And by any chance, can you go over one of the homework questions?
Sure. What would you like me to go over?
It was, I think it was 4 point, I have it written. It was 4.5. Oh no, 4.6.
Do you have the question?
Yeah. It says 4.6, number 2. So it's just the level curves for barometric pressure. It shows like a map, like a geographic map, and it asks you to estimate a value of directional derivative. But it gives, so it says a deep low with pressure 972 MB is moving over northeast Iowa. The distance along the red line from K to S is 300. And then it just asks you to estimate the value.
Okay. So we got. What number is it? 2?
Yeah.
So it says level curves are shown. Okay, and so we're going from K to S. Okay, it says what are the units? Okay, so MB per kilometer. Okay, deep low, so a deep low pressure with 972. Distance along the red line, okay, is 300. So that's just average rate of change, right? So estimate the value of the directional derivative. So level curves are shown 6 a.m. on a deep low with 972 is moving over northeast Iowa. Okay. Oh, they give us what the level curves are here. Okay, so at S, it's 976, and at K, it's at 1,000, right?
Yeah.
So you're gonna do,
Subtract and divide.
yeah, you just subtract and divide by 3,000.
Okay.
That makes sense?
Yeah, it makes sense. Thank you.
Okay. So yeah, it's just your average rate of change. I haven't even covered that yet, Azmeen.
Okay, that's fine then.
I might cover that today. Okay, 14.7 and 14.8 today. Showing people. It's still sharing the screen. Okay, good. Oh, there we go. Okay. Okay, 14.7. Maximum and minimum values, max and min. In 3D. Okay, max and min in 3D. Okay, maximums and minimums in 3 dimensions. Okay, a function with 2 variables has a local maximum at AB if f of xy is less than or equal to f of AB when xy is near AB. Okay. Okay, this means that f of xy is less than or equal to f of AB for all points in some disk with center AB. Okay. Similarly, if f of xy is greater than or equal to f of AB when xy is near AB, then this is a local minimum. Okay, so what is this saying? It's saying, look, we have a surface here. Okay, and we're going to say that this is the maximum value. Okay, and we're going to draw a disk around this. Think of it as like a neighborhood. In the neighborhood of AB, okay, it means that for all the points that are near AB, all of these points that are in this neighborhood, if it's a maximum, then AB beats out all the other points, beats out all the other values, okay, for the function. That's all it means. Okay, if every other point is smaller, if all of the f of x, y's are smaller, then AB is the maximum, right? If all of them are bigger, right? If all of them are bigger, say we have this, right? If all of the points are bigger on this surface, okay, if all of them are bigger, then it's a minimum. Okay. Minimum if all the other points in the neighborhood are bigger, then it's a minimum. That's all it's saying. Okay, then it's a local minimum. Okay, let's look at a theorem here. Okay, if f has a local max or local min at AB, okay, at point AB, and the first order partial derivatives exist, and the first order partial derivatives exist, there, okay, at AB. Then f sub x of AB is equal to 0, and f sub y of AB is equal to 0. Okay? So basically, we're extending what we know in 2 dimensions to now 3 dimensions. Hey, look. Okay, remember when we had 2 dimensions? How did we find a maximum value? Well, that's when the derivative was equal to 0. Well, how are we going to extend that to 2 dimensions? Well, now we're going to be going in both directions, and we want to find the derivative in the x direction is equal to 0, and the derivative in the y direction is also equal to 0. Okay, so we just extend it to the same definition, but same concept, but now, okay. If this is true, if f sub x is equal to 0 and f sub y is equal to 0, boom, that's going to be a max or min, right? It's maximum or minimum value. Okay, so we could say this is a, in the x direction, in the y direction. So we would say this is f sub x, and this is f sub y, and our derivative is where this thing, where these partials are equal to 0. Okay, we're kind of taking, 2 dimensions. We're just extending it out to a 3rd dimension. Okay, you can think of this like the z and the y-axis, right? And we would say, what would be the max here? Well, that's when the derivative, right, f prime of z, f prime of y would be equal to 0, right? But now think about extending this not as a line, but as a sheet, right? So we would actually, it would look more like this. We would extend this out like this so that it's a sheet. And you'd be like, oh, well, now where is this maximum occurring? Well, it occurs along this, that there, we could have, some maximum value. And so you're like, oh, well, this is f sub x, okay, of xy is equal to 0, and f sub y of xy is also equal to 0. Okay, so it's a horizontal tangent in the x direction and the y direction, basically what we're saying. Okay, where's the horizontal tangent in the x direction, and where's the horizontal tangent in the y direction? And where those two are the same, that's our maximum or minimum. Okay, let's do one. Oh, and if this is true, then the point AB, okay, the point AB is called a critical point. Critical point. Of f. Okay, so number 1, find the extreme values of f of xy equals x squared plus y squared minus 2x minus 6y plus 14. Okay, let's find the extreme values. Let's find the mins and the maxes here. Okay. So what do we want to do? We want to find out, well, what's f sub x? What's the partial with respect to x? Well, that's 2x minus 2, right? And what do I want to do with that? Well, I want to set that equal to 0. Oh, okay. So that's going to be 2x equals 2 divided by 2, x equals 1. Okay. Okay, what about f sub y? Well, what's this going to be? This is going to be 2y minus 6. set that equal to 0, and y equals 3. Okay, so get rid of this. You guys know how to do simple algebra. Okay, so what do we have? We have the function, okay, the derivative, partial derivative is equal to 0 when x is 1. The partial derivative of, with respect to y is y equals 3. So we know that that AB, or 1, 3, is a critical point of f of x, y. Okay. So what's the value here? What's the value of this? Right, well, what's f of 1, 3? What's f of 1, 3? Well, okay, let's see what we got here. So 1 squared plus 3 squared minus 2 times 1 minus 6 times 3 plus 14. Okay. So if I plug all that into a calculator, I would get 4. Okay, so 4. So the problem is, what? What's the problem here?
It doesn't equal 0.
Nope, that's not the problem. I have this point out in space at 1, 4, at 1, 3, 4, right? 1, 3, 4. Okay, what's the problem? I know it's a critical value.
We still don't know what it represents. We would need to do fxx and take the derivative again and see if it's a minimum, a maximum.
Yeah. We don't know if it's a minimum or a maximum, as Neen says. We don't know if this is concave up or concave down, right? We don't know if it goes like this or like this. Does that make sense? We know that it's one of the two. But we don't know. And we don't have the tools yet to do this, so I'm gonna cheat a little bit and just analyze the function. Okay, so let's analyze the function that we have here a little bit. Okay, so let's complete the square on this one and see what we get. Okay, is it going to be concave up or concave down? Okay. Okay. So we have f of x, y is equal to x squared minus 2x. Let's go back to the original. What was the original? Okay, that's fine. X squared minus 2x. I'm going to complete the square. That means I have to add 1 and subtract 1. Okay, y minus 6y. I'm going to have to add 9 and subtract 9. Right, and then add 14 at the very end. Okay, so what is this going to become? Well, this becomes x minus 1 squared plus y minus 3 squared plus 4, right? Is equal to what? Is equal to f of x, y. Okay, kind of cool. Okay, so if I set y equal to k, what would I get? I would get the equation of a circle. Does that make sense? My level curves there are circles. Does that make sense? They're just differing size radii. If I let this equal k, my level curves are circles, right? Circles. Okay. And so is this going to be a maximum or minimum? Well, if I look at this, isn't anything squared positive? Anything squared is positive, correct? And then, so this is positive, and this is positive. Which means that the lowest value that this could ever take on is what? What's the minimum value that I could ever have here?
0?
No, 4.
Oh, yeah, sorry.
Okay, 4. The minimum value that this could ever take on is 4 because everything would end up being positive. And where would it be 4? Where would the function be equal to 4? It would be when, yes, when this is 0 and when this is 0. And what values make that 0? Well, how about 1, 3? So I get my 0 at 1, 3. And my minimum value is 4. So what is this? This is a local min. So a local minimum, so it looks like this. Right? This is an elliptic paraboloid. Okay, elliptic paraboloid. Okay, where the ellipses are actually circles. So it's just a cup. It's a cup opening up, right? Does that make sense? So what is this? This is local minimum. Okay, local minimum. Okay, now let's jump to what, how do you say your name? Ismene?
It's Eastman.
Eastman.
Yeah.
Thank you for clarifying. So we're only into like week 6. So that's all. Okay. So let me say it one more time. Eastman?
Eastman.
Eastman. Okay. Like Eastman.
Yeah, just Eastman, yeah.
Eastman. Okay. I'll just say it like that. Eastman. Okay. So have you taken business calc, Eastman?
No, the last calculus class I took was AP Calculus BC.
Oh, BC. Okay. Okay. So I was just wondering if you have ever heard of the D test or the second derivative test.
Yeah, I've heard about it a little bit, yeah.
A little bit. Okay. So okay. Because that you're kind of like jumping the gun a little bit. So let's talk about the D test. Okay. The D test. Okay. Second derivative test here. Okay. Which is the D test. Okay. This is the second derivative test. For 2 variables. Okay, second derivative test for two variables. Okay. So suppose the second partial derivatives of AB okay, suppose the second partial derivatives of AB okay, exist. Okay, and f of x of AB is equal to 0. And f of y of AB is equal to 0. Okay, then let D equal, okay, f sub xx evaluated at AB, okay, times f sub yy evaluated at AB, minus f sub xy evaluated at AB squared. Okay, then we let that D, this is going to be some value D, we're going to calculate if, okay, if D is greater than 0, which means if D is positive and the second partial with respect to x is positive, then f of AB is a local minimum. Go away. Okay, then f of AB is a local min. Okay. What about B? Okay. If D is greater than 0 and the second derivative is less than 0, okay, second partial derivative with respect to x is less than 0, okay, then f of AB is a local max. Okay, so if x is concave down, but d is greater than 0, then it's a max. Okay, so think of it as concave down. Okay, and let's think of this as concave up. Okay. Okay. Now, what happens if d is less than 0? Okay. Well, see. If d is less than 0, then f of AB is called a saddle point. Okay, and we'll talk about what that means in a little bit. Okay. And then what if d was equal to 0? Then it's inconclusive. Okay, then it's inconclusive. We don't know. Okay. So what's a saddle point? Well, I think we talked about this before with the hyperboloid. Okay, we have this going in this direction, this going in this direction. Okay, and basically it's a saddle. Okay, so okay, and so we have this coming down like so. Actually, it doesn't look like that. Okay, it connects to here. Okay, and it goes up. Okay, and it's going up on one end. Let me get rid of this. This is bad. It's bad. Okay. So it folds down like this. Okay. Okay, and it's a saddle. Okay, think of it like a saddle. Okay, so okay, it goes up, but and as it comes out, it folds down, and it's a surface. Okay, let's just leave that off. It's making me not happy. Okay, so it's a saddle. So this goes like this, really, like this. Okay. It's coming down like this. Okay, so in one direction it goes up. Okay, in one direction it goes up, and the other direction it goes down. Okay, so one direction it goes up. In this direction it goes up, and in this direction it goes down. Okay, so we'll say that this is the y direction. The y direction it's going up. Okay, if I travel in the y direction here, I go up. Okay, I go up along this surface here. Okay, if I travel in the x direction, however, I go down. Okay, and so if d is less than 0, then it's a saddle point. That is the saddle point thing. This means that the partial in the x and the partial in the y are bigger than the partials in the xx or yy. Okay, take the partial on x with the partial on y, that's a bigger value than taking them individually, xx and yy. Okay. Okay, let's do this with the last value that we got. Okay, what did we have before? Let's use the one that we had before. We had f of xy equals x squared plus y squared minus 2x plus 6y plus 14, right? Okay. So this, we said that the f sub x here was equal to 2x minus 2. We said f sub y was equal to 2y, I think it was minus 6, right? Minus 6. So what's f sub xx? What's f sub xx? Well, that's just equal to 2. What's f sub xy? Well, that's equal to 0. There's nothing. What's f sub yy? Well, that's equal to 2. Okay. So let's see what happens here. So d is equal to f sub xx times f sub yy minus f sub xy squared. So what is this? This is 2 times 2 minus 0 squared, which is 4, which is greater than 0. Okay, so we know that we have a local min or a local max because d is greater than 0. Okay, minimum, maximum. We don't know. Well, what's going to tell us? What's going to tell us is this thing concave up or is this thing concave down in the x direction? Well, let's see. If f sub xx is greater than 2, then we know it's concave up, which means that what? It's a minimum. And that's exactly what we found out, right? We found out that this thing was a local minimum at 1, 2, 4, I think it was something like that. Or 1, 3, 4. We have a local minimum, right? Woohoo. There we go. Okay. Sounds good. Okay, let's do one that's a little bit more interesting. Okay, fine. I used to say more challenging, and I used to freak students out. They don't like that word, more challenging. So now I just changed it to more interesting. Okay, and if I really want to go like the extra mile, I just say we're going to spice things up, make it spicy. Everybody likes spiciness. I mean, everybody likes, you know, to throw a little jalapenos on your salad, right? Just like, let's just spice it up. Okay. It's all about how you say things, right? So instead of saying like no parking, you could say park elsewhere, right? So it's all about the way you phrase it. Park elsewhere, right? Okay. So anyway, I digress. Find the local extrema of f of xy equals x to the fourth plus y to the fourth minus 4xy plus 1. Okay, so we want to find the local extrema here. Okay, we want to find the mins and maxes, right? Okay, so what are we going to do? We're going to say, okay, what's f sub x? Well, that's 4x cubed minus 4y, right? Okay. What's f sub y? Well, that guy is going to be 4y cubed minus 4x, right? Okay. And what do we want to do? We want to set these equal to 0. Okay, because that's where our mins and maxes are going to live. And these things are equal to 0, right? Okay. So what do we want to do? Well, let's do a little substitution here. Okay. So we'll do a little substitution. So here y is equal to x cubed, is that right? Okay, y is equal to x cubed. Okay, so what I'm going to do is I'm going to take this, I'm going to sub it in for y here. So I get 4 times x cubed minus 4x is equal to 0. Okay, so this is 4x to the 9th minus 4x equals 0. I'm going to factor out a 4x. So I get x to the 8th minus 1 equals 0. I'm going to factor this bad boy. He's going to be 4x times. Okay, x to the fourth minus 1 times x to the fourth plus 1. So this is going to become x squared minus 1 times x squared plus 1 times x to the fourth plus 1. Okay, equals 0, 4x. Okay, and then this thing here in the front will get factored. This will get factored x minus 1 times x plus 1, right? Times x squared plus 1 times x to the fourth plus 1 equals 0. Okay, so what does this mean? This means that x equals 0, 1, and negative 1. Okay, which means that what would y equal? Well, if x is 0, then wouldn't y equal 0? Yep. Okay, there you go. I put the little eyebrows on that because it always makes me, this makes me think that this guy's like an owl. Okay. Owl who? Owl you. There you go. 0, 0. Okay. I see weird things. Okay. At least I don't see dead people. I see dead people. Okay. Anyway, that's an old reference.
How'd you get to 0, 0 again?
How do I get the point 0, 0? Because I factored. What's going to get me zeros here? 0, 1, and negative 1.
Okay, got it. Thank you.
That whole algebra factoring stuff. Okay, so 0, 0 is a point. Okay, what else is a point? How about 1, 1? Isn't 1, 1 a point? Plug in 1 in here and you get 1. And what about negative 1, negative 1? Isn't that also a point? Yeah. Okay, so we've got actually 3 points to test. Okay, we've got 3 points to test. Okay, so let's look at f sub xx, f sub yy, and f sub xy. Okay, so before we had f sub x was what? F sub x was 4x cubed minus 4y. Okay, so let's take the partial again with respect to x, and what do we get? We get 12x, right? 12x squared. 12x squared. Okay, what about, go away, dude. Okay, what about yy? What's yy going to be? Well, that's going to be 12y squared, right? 12y squared. Okay, and what's xy? What's xy? Well, that's going to be just negative 4. Yeah, negative 4. Okay, so we have 3 points to test. We want to test 0, 0. Okay, so for the point 0, 0, we need to find the d score. We call this a d score, or d value, or whatever you want. Okay. Okay, so what's the d value here? Well, this is going to be 12 times 0 squared, right? That's going to be for my x. This is f of xx. Well, you guys haven't memorized it yet. So f of xx, f of yy, minus f of xy squared. Boom. So what's this going to be? Plug in the 0, right? So this is 12 times x squared. But what is x? In this case, it's 0 times 12 times y squared, which is 0. Okay, minus 4, right? Plus negative 4. Or plus negative 4 squared. Okay, so this is going to be equal to 16, which is positive. Okay, so this is going to be a local, all right? Is this minus? No, it's minus. This should be a minus sign, sorry. So this is minus negative 4 squared. It's a minus sign. Okay, minus negative, so this is a minus 16. Messed up on the minuses there. So minus 16. So this is d is less than 0, which tells me it's a saddle point. Okay, so that's a saddle point. 0, 0. Okay. Okay, what about 1, 1? Let's try 1, 1 here. Okay, so D is equal to 12 times 12 minus negative 4 squared. Okay, so this is going to be 144, right? Minus 16, which is 128, which is greater than 0. Okay, so that's greater than 0. But what about f of xx? Well, f of xx is equal to 12, which is greater than 0. So since this is greater than 0, okay, that's concave up. This is greater, D is greater than 0. It means that there is a local exists. Okay, and this means that it's concave up, which means that it's going to be a local minimum. Okay, so we say f of 1, 1, okay, which if you plugged 1, 1 into the original function, you would get negative 1 as your answer. And so we'd say f of 1, 1 equals negative 1 is a local minimum. That's a local minimum. So, okay, what about D for negative 1, negative 1? Well, this is going to be equal to 12x squared, which is negative 1 squared times 12 times negative 1 squared minus negative 4 squared. This is again going to be 144 minus 16, which is 128, which is greater than 0. Therefore, at negative 1, 1, this is also a local minimum. How is it also a local minimum? Let's look at f of xx. Well, what is that? That's 12 times negative 1 squared, which is 12. That's greater than 0. So it's also a local minimum. So how can you have two local minimums and then a saddle point? It's kind of weird, right? Well, I don't know. It's kind of like if I had something like this, and something like this, and then maybe connected in between, right? And then, right? So, and then maybe it went down like this, down like this, and then went out like that, right? That makes sense? So you have kind of like these minimums here, and then you have a saddle, right? So this would be at 1, 1, negative 1, and this would be at negative 1, negative 1, negative 1. Something like that. Okay, because f of negative 1 is also negative 1, which is also a local minimum. So, yeah. We have our saddle. Okay, we have our saddle. But we also have these bowls here. Okay, and so you get the idea. Okay, extreme values. So let's talk about the extreme value theorem. For two variables. Okay, two variables. Extreme value theorem for functions of two variables. Boom. Okay, so if f is continuous on a closed bounded set, D in R2, okay, in R2. Okay, why is D in R2? Well, D is the domain. Okay, think of that. Think of that. D is domain here, not. Okay, D is domain, not a value. This isn't the D score. Okay, this isn't the D test. This is just the domain. Okay, in R2. Okay, why is it the domain in R2? Well, if you have a surface in R3, what is your projection onto the XY plane? Well, it's going to have some sort of projection onto the XY plane, and that's going to be your D, or your domain in R2. Does that make sense? So it's like flatland. I don't know if you guys ever know what flatland is. Anybody know what flatland is? Heard of that reference at all? No? Well, Flatland is a book. I probably even have the book. My son, no, I think my son stole it. Yeah, he stole it. Flatland is about this two-dimensional object that goes and visits the three-dimensional world, and how he's just a shadow of the people, and how his two-dimensional world differs from a three-dimensional reality. So it's a good book. So there's a couple movies made on it, on that premise. But your three-dimensional world, it's Flatland. It's a good like one-day read. It's really easy to read. Let me see if I can go get it. Tell you who the author is. One second. Like I said, it'd be a good thing to kind of help you visualize this stuff, but it's Flatland. It's called Flatland by Edwin Abbott. So a romance of many dimensions. Again, it's like a easy one-day read. It's like a 136 easy pages. It's really thin. So Flatland by Edwin Abbott. I would highly encourage you to read this. Okay, so you can start visualizing this stuff and say, oh, how is the projection of the three-dimensional world go onto the two-dimensional? Because we're going to talk about domain and range a lot. Okay, come chapter 15 and 16, it's all about domain and range. Okay, so again, it's like I said, it's an easy one-day read. It's very small. Okay, so if F is continuous on a closed bounded set D, which is the domain, okay, in R2, then F attains an absolute maximum value okay, F sub x1, y1, and an absolute minimum value F sub x2, y2 at some points okay, x1, y1, x1, y1, and x2, y2 in D, in the domain D. Okay, so it's just saying, look, okay, if I restrict my domain, right, if I restrict my domain, let's take this sheet, okay, in 3 space, and I'm going to restrict my domain to just this sheet here. Okay, it's restricted. Okay, I'm going to say, so what would the domain be? Well, it'd just be a rectangle, right? The projection of this would just be a rectangle. We'll call that D. And we're saying, look, at some point, there's going to be a maximum value and there's going to be a minimum value. Think of this as absolute max and min. It's analogous to absolute max and min. Right? What's your absolute max and min? Well, there's got to be one because it's a closed bounded set. Okay, we're just saying, look, absolute max and min, right? How did we get absolute max and min? Well, when we cut off our domain and we said, well, the domain is AB. Well, here we're just saying that we're restricting our domain, therefore we're forcing there to be an absolute max and absolute min. Okay? And you can calculate those. You can find the mins, you can find the maxes. You'd have to find the edges, the 4 points along these edges, and you'd have to calculate 1, 2, 3, 4, 5, 6 points here. Okay, and then you have to find out, well, which one's the lowest and which one's the highest. And that would be your absolute or your extreme values. Does that make sense? Yeah. Okay, let's get into something a little funner. Okay, let's talk about Lagrange multipliers. Okay, 14.8. Lagrange multipliers. Okay, linear algebra. Woohoo! Linear algebra time. I don't know why I'm so excited today. It shouldn't be. I think it's the pizza I ate for lunch. I don't normally eat pizza for lunch, so I think I have a little bit more energy today. All those carbs going straight to my head. Okay, so if f of x, y, z is z, hello? Okay. Scary. Okay, and g of x, y, z is equal to k, then the level surface of g tangent to the maximum value of f, okay, produce parallel gradient vectors of both f and g. Okay, that is the gradient of f of x naught, y naught, z naught is equal to lambda, or some scalar multiple, right? Because if they're parallel, then then these gradients, okay, are going to be going the same direction, and so they're just going to be scalar multiples of each other. Okay, think of two vectors that are going in the same direction. Well, what would those two vectors have to be? They'd have to be scalar multiples of each other, right? Okay, so the level surface of G tangent, so the tangent, the level surface of G tangent to the maximum value. So we found the maximum value. Okay, produce, okay. Okay. I could just say, I'm not going to say maximum, I'm going to say extreme value. Because there could be more, okay, more than one. Okay, tangent to the extreme values of f, Okay, produce parallel gradient vectors. Okay, lambda delta, or sorry, del G of X naught, Y naught, Z naught. Where lambda is called a Lagrange multiplier. Okay, so our goal, okay, your mission, should you choose to accept it, is to figure out what lambda is or get rid of it. Okay, so find out what lambda is or eliminate it altogether. Okay, to find, okay, the maximum and minimum values, the maximum values of f of x, y, z, subject to the constraint. Now you got to know what's the constraint and what's the function on this. Subject to the constraint g of x, y, z equals k a. Okay, here's step A. Find all values x, y, z and lambda such that the gradient of f of x, y, z is equal to lambda times the gradient of g of x, y, z, and okay, it's subject to this constraint. I'll call this constraint number 1 and constraint number 2. You have to have both. And constraint number 2, which is the original g of x, y, z equals k. It's got to satisfy both of these, not just one of them. It's got to satisfy both. And if it satisfies both, you got your maxes and mins. How? Well, we just evaluate all the points. Okay, evaluate f at all points x, y, z from step A. The largest of these values is the maximum. And the smallest is the minimum. Okay, so
Can you scroll down just a bit?
sure. I want to see which one I want to do first. Yeah. Okay. Whatever. let me try this one. I haven't tried this one yet. This might be an interesting thing to do. Is it subject to a constraint though? That's what I gotta think. Gotta think about this for a second. No, it's not. It's not subject to a constraint. Okay. Okay. That takes care of that. Okay, let's go into an example here. Example 1. Okay, find the extreme values of f of xy equals x squared plus 2y squared on the circle x squared plus y squared equals 1. Okay, so you're like, Well, the original one said, hey, we had f of x, y, z. Where the hell is z? Can I say that? Am I allowed to say hell? Maybe I'm not allowed to say that. Okay. Where the heck is z in this case? Well, it's right here. But then you're like, but that's f of xy. That's not f of xyz. Well, what if I did this? What if I said that this was z equals x squared plus 2y squared. And then I said, well, what if I subtracted z from both sides? And I said 0 is equal to x squared plus 2y squared minus z. Right? Okay. And then in this case, if this was g of x, y, z, well, what is z and what is this thing? G of x, y, z is equal to 1. Okay, and then in this case, well, what is z? Z is 0, right? Z is 0. Okay, in this case here, z is 0. Okay, so what we're doing is we're doing this. Okay, this is what we're doing. We're saying, give me this surface. Okay, give me a surface here. Okay, and then I'm going to restrict this surface to the what? To the unit circle, right? Here's the unit circle, right? And so if we talked about g of x, y, z, this would be g of x, y, 0, right? Because it's on the plane z equals 0. And so what are we doing? We're saying, well, if we restrict the domain to this, then we're restricting, we have a constraint here for this region. And we want to find the max or min on that region, in that circle on the surface. Oh, okay, so this is D, right? This is my domain. Okay, that's the domain that's being restricted here. And so we're guaranteed that in that domain, there's going to be a max or min. Oh, okay. So there's a max or min guaranteed on that domain. Okay, it could be on the edge. It could be in the middle. It could be anywhere. Okay, in that domain, but I'm guaranteed at least one max and min. Okay. Okay, so what do we want to do here? Well, we want to find del of f, okay, del of f of x, y, z equals lambda del of g of x, y, z. Okay. So we want to take the partials, right? The partials. Okay, so let's do that. Okay, so we have f of x, y, z here, right? Okay, is just that's equal to 0. Okay, so let's take the gradient, right? The gradient. So the partial on x, 2x. Partial on y, 4y. Partial on z, -1, right? -1. Okay, and the gradient is a vector. Okay, equals lambda. Okay, times, what's the gradient of g here? G. Okay, well, g is going to be, right, it's going to be x squared plus y squared plus 0 squared is equal to 1. Okay, so what's the gradient with respect to, what's the derivative with respect to x? It's 2x. Okay, what's the derivative with respect to y? That's 2y. Okay, and what's the derivative with respect to z? That's 0. Okay, 0. Okay. Okay, so let's take a look at this for a second. Okay. Okay, so I can match these up. I can say this is, okay, 2x is equal to lambda 2x. Okay. So in this case, okay, this can only be true under 2 conditions. This can only be true under 2 conditions. And that condition is, okay, that lambda equals 1, or, okay, or that x equals 0. Okay, so either lambda is equal to 1 or x equals 0. That's the only way that these two can match up. Okay, this first term and this first term. Okay, okay, what about the next one here? Okay. Well, 4y okay, 4y is equal to lambda 2y. Okay. So in this case, okay, in this case, okay, what is true? Okay, in this case, either y is 0. Okay, y is 0. Okay, or lambda is equal to 2. Okay, or y is 0. Okay. Okay, and then what about the last case here? The last case, that's kind of weird. Okay, -1 is equal to lambda times 0. That doesn't even make sense. Okay, -1 is equal to lambda times 0. Well, that means that 0 would equal -1. Okay, so that doesn't make sense for any lambda. Lambda equals what? Okay. So we're gonna test these cases independently of each other. Okay, we're gonna kind of narrow this down. Okay. If x equals 0, because lambda, we don't know what lambda is. Lambda is kind of like out there. It wants to be 1, it wants to be 2, it wants to be whatever. Yeah, it's kind of messing with me, right? So what do I know is true? Well, and know that if x is 0, then this works. If y is 0, then this works. Okay, lambda, all bets are off on lambda at this point. Okay, so if x equals 0, then what? Then x squared, subject to the constraint, right? Then x squared plus y squared still equals 1. Then 0 squared plus y squared equals 1. Then y squared is equal to 1. That means that y equals plus or minus 1. Ah, okay. So if x is 0, then I get 0, 1 or 0, negative 1. Oh, okay. Okay, that helps. Okay, what if y is equal to 0? Then I get x squared plus y squared equals 1. And if y is 0, then x equals plus or minus 1. Ah, okay, so the other 2 points that I would work with are negative 1, 0, and 1, 0. Boom. So these are the only the 4 points that make any sense that I can test. Okay? The only ones that make sense. So I'm going to test all 4 of these points in my original function. What was my original function? It was f of xy equals x squared plus 2y squared. Okay. So I'm going to try f of 0, 1. Okay, so that's going to be 0 squared plus 2 times 1 squared. That's 2. Let's try f of 0, negative 1. That's equals 2 as well. Okay, what about f of 1, 0? Well, that's 1 squared plus 2 times 0. That's what's 1. And what about f of negative 1, 0? That's also 1. Okay. So what's the maximum value that I'm going to get? What's the maximum value? Well, I'm going to get a maximum value of 2. And what's the minimum value I'm going to get? 1. So the maximum value on this function is 2. The minimum value is 1. Okay. Where do these occur? They occur, okay, at 0, 1, 0, negative 1 for the 2's. Okay. So remember, x's are zeros, right? So at 0, 1, and then 2. So think of this as 0, 1, 2 at point 0, 1, 2, and at point 0, negative 1, 2, I have my maxes. And at 1, 0, 1, and at negative 1, 0, 1, I have my mins. Oh, okay. So if we look at a graph here, okay, so where is 0, 1, 2? 0, 1, 2, these are zeros in the x's. So y is out 1, in the y's, and then up 2. So I've got my maxes here. Okay, so these are my maxes. Okay, and then where's my mins? Where do my minimums exist? Well, my minimums exist when y is 0, but we're out 1, 1 and negative 1 in the x direction. So we've got some minimums here and here. Okay, so again, I don't know what the surface is going to look like, but in the x direction, I've got minimums. In the y direction, I've got maximums. Okay. That's good. Okay. Okay. I don't know what this thing looks like. It'd be interesting to see, though. If I could find the right app. 3D calculator. Let's see what this does for me. Close. I don't want to. Can I do this? Can I do f of x, y? It's going to let me do this. F of x comma y. Where's the comma? Comma, 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 comma. xy equals is there an equals on my keyboard? No. Equals. Okay, and then okay, x. What was this? X squared plus 2y squared. X squared. I'll get the right keyboard here. X squared. Ooh, that's pretty. Plus, okay, plus what? Plus 2y squared. 2y squared. Squared. Boom. Okay. So it's interesting. Okay, subject to what constraint though? What constraint? Input. Okay, so subject to the constraint x squared plus y squared equals 1. I don't know if that's gonna, oh, that's an exponent. Equals 1. Oh, ooh, look at that. Isn't that pretty? Isn't that pretty? It's a cylinder. Sweet. So, this is nice. Okay, we can see, if I orient this properly, okay, that look at where the minimums are, where the minimum values are. The minimums are along this red axis. Okay, look at that. The minimums, look at that. The minimum is along the red axis. And I'm to assume that, okay, that's at 1. Okay, the minimum value is at 1. Okay, which it is. Like, look at it here. Boom. Z equals 1. Minimum value at 1. Nice. Nice. Okay, and then where's the maximum value? Oh, look at that. Maximum value is long. Oh, I can make it spin too. Look at that. Okay, so am I sharing my screen? I'm not sharing my screen.
I was just gonna ask if we're supposed to be seeing it.
Ah, you're supposed to be seeing it. Sorry. What the heck? Okay, stop the sharing. Sharing is caring. So here we go. Boom. Prepare to be so that's a nice graph, right? So as you can see, the cylinder is the domain. That's the red. The paraboloid is the blue. Okay, and let me stop spinning for a second, getting nauseated. You can see that the maximum in this domain is going to occur where? It's going to occur at 2. The maximum value where the red and the blue combine is 2. What's the minimum value? It's 1. It's amazing. Let me spin it. Let me spin it. Spin. Spin. Spin like you mean it. Does that make sense? Isn't that kind of cool? I think it's kind of cool. Like, bro. It makes sense that it's at 1 and 2. Okay, along the x-axis is the 1. That's the red axis there. Along the y-axis is the 2. Anyway, I don't know. If you guys aren't impressed, then there's no hope for you. Whatever. And this is GeoGebra 3D calculator. If you want to do this yourself, just go to GeoGebra 3D calculator. You can plug that in yourself. Okay, makes sense? Okay, let's do one real life example before we leave today. Okay, let's see how this thing works out in the real world. Okay, of optimization. Let's talk about optimization for a second. Okay, real life example here. Optimization. I'm just gonna let that spin for a little. It's pretty. It makes me happy. Look at that. Ooh, disappeared. There it comes back. Perfect. Okay, I'm gonna stop the sharing. Stop sharing. Boom. Okay. Go back to sharing my screen here. Okay. Okay. Question? No? Okay, a rectangular box. I don't know what example you want. Number 2? Number 2. Example 2. Okay, last example. Okay, number 2. Okay. A rectangular box without a lid is to be made from 12 square meters of cardboard. Find the maximum volume of such a box. Okay. Find the maximum volume of such a box. I've got 12 square meters of cardboard and I want to fold this up and use it for a box with no lid. So how can I do that? Any ideas on how I can?
You could use the equation for volume, but do like V equals X times Y times Z.
Yeah, there you go. Okay. Are you reading the book? Is that what's going on here?
Yeah, I am.
You are. See, you're just like, I know the answer because I read the book. I read the book already. Exactly. Yeah, you think she's all smart and stuff. She just reads ahead. I guess that's smart, but okay. So yeah, let's do that. So, delete. Where's my delete key? Delete you, sir. Guess I can't delete you. Can I move you? Can I delete and move you? Can I stop you? No. Delete. There we go. Proofing. I don't want to proof. I want to ignore. I don't want to delete. I want to go away. There we go. Okay. So find the maximum volume of such a box. So what's the volume of a box? X, Y, Z, right? I'm going to orient the box so that it's along the X, Y, Z axis. Okay. Actually, I'm not going to do that. I'm going to go here. There. Okay, there's my box, right? X, Y, Z. Okay, so the volume is x, y, z. So this is my f of x, y, z. That's what I want to optimize. That's what I want to find the maximum. I want to find my max of this. Okay, and what's my constraint?
The 12 meters squared.
Yeah, and that's my surface area, right? So how would I find the surface area of this box? Well, I'd have to find the area of each side and add it all up, right? So what's the area of the base? XY. What's the area of the sides? It's 2YZ plus 2XZ, right? Does that make sense? And we said that that was equal to 12. So that's the constraint. Okay, so now what do we want to do? We're going to take delta F, or sorry, del F is equal to lambda del G, right? Del G, okay. So what's del F? Well, that's the partial. That's F sub X, F sub Y, F sub Z is equal to lambda G sub X, G sub Y, okay, it's the gradient, G sub Y, G sub Z. You think all these smart people are just born smart. I don't think it really works that way. I'm not any smarter than any of you people. Okay, you think, oh, this guy teaches Calc 3. No, I'm not. I'm no smarter than you guys. I just know exactly where to get the information from when I need it. Just like Eastman here, she knows exactly where to get the information that she needs. So that's the only difference. It's not, you're not born with this stuff. Okay. So you can't teach a 5th grader multivariable calculus, although most of them, maybe some freak of nature out there you can, but it's just not going to happen. Okay. It's learning how to learn, right? You got to learn how to learn. You also got to learn how to think for yourself. That's a hard concept in college, is teaching people how to think for themselves. Like, are you going to listen to some person tell you what to do all your life? Are you going to start thinking for yourself? So anyway, it's just me ranting today. I'm rambling. Okay, let's get our partials here. Okay, what's f sub x? What's f sub x? What's the partial with respect to x? Anyone? Anyone? Bueller? Oh, Armando. Good. Thank you. Okay. Anyone? Anyone? No. Anyone? Good. That's a Ferris Bueller throwback right there. Okay. Throwback Wednesday. Okay, so this is Ben Stein is his name. Made him famous. He was an economics professor, and they walked into his lecture and said, "Hey, could you read these lines for this movie we're making, Ferris Bueller?" And he's like, "Sure, why not?" And then he became wildly famous. He's like, "I was just teaching economics." He has a PhD in economics. He's an economics professor. He became wildly famous. Really? Okay, anyway, I digress. So yes, it's YZ. YZ. Okay, what's f sub y? XZ. What's f sub z? XY. Boom. Done. What's g sub x? What's g sub x? Well, g sub x is going to be 2z plus y, right? 2z plus y, or y plus 2z. All right. Okay. Yeah, because this thing doesn't have an x. There's no x in the second term, right? So if I take the derivative of the first one with respect to x, that's y. If I take the second one with respect to x, or the third one with respect to x, that's 2z. So this is going to be x plus 2z. Let's do g sub y. Okay, g sub y. That's going to be x. Okay, x plus 2z. Okay, x plus 2z. Well, this should be y, I think. The first one should be y. Yeah, this should be y. Sorry. It's y, right? With respect to x, you get a y. Okay, 2z. And then, what's the last one here? With respect to z, well, there's 2x plus 2y. Plus 2y. Okay. Nice. Okay, so now let's set up our linear equations. I'm going to say that this is going to be, if I distribute the lambda, okay, I get yz equals lambda times y plus 2z. I get xz equals lambda times x plus 2z. And I get xy equals lambda times 2x plus 2y. Okay, just matching component to component. Okay, so now I'm going to do something sneaky here, in that I want to solve for lambda or x or y or something, try to figure out what's z with respect to the what's x, y, and z with respect to these constraints, right? What's going to give me my maximum values? What are my maximum dimensions here? What are the dimensions that's going to create a maximum volume? What are the x, y, and z that are going to maximize this out? So I'm going to try to set these three equations equal to each other so I can eliminate some variables. Okay. Okay, so I'm going to do something sneaky here. I'm going to do this. I'm going to say that this is x, y, z. I'm going to put an x there, and then I'm going to go y x z. I'm going to put a y there. Then I'm going to put z x y, and then I'm going to put a z there. And what does that allow me to do? It allows me to set all three of these equal to each other. Oh, that's kind of cool. Yeah. And that actually allows me to eliminate lambda. Because if all three of these are equal to each other, then and lambda is just a multiple of each of them, then I could divide by lambda, and I could just set each of these equal to each other. Okay. I could say that lambda x times y plus 2z is equal to lambda y times x plus 2z is equal to lambda z times 2x plus 2y. Cool, 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 cool. Okay. Yeah. Okay, let's cancel out the lambda. And what do we get? We get xy plus 2xz is equal to xy plus 2yz. Ooh, that's interesting. Is also equal to 2xz plus 2yz. That's interesting. Okay. So what does this tell me? Well, let's look at the first two here. What is this going to tell me? This is going to tell me that, well, these are going to cancel. And if I divide by 2z, I get x equals y. Oh, okay, so x has to be equal to y. Okay, that's kind of cool. Okay. So then if I use that information in the last one here, right, then this becomes, let's set the last two equal to each other. Let me get rid of this. Okay, so this is going to give me that, right? Okay. So I'm going to say that x is equal to y. Okay, that's kind of, I want to solve for z though. I want to solve for z. How can I solve for z? Wait, we forgot an equation. We forgot an equation. What's the fourth equation here? Oh yeah, the fourth equation is this guy. It's the surface area equation. 2xz, that's the constraint. It's the constraint. We know that x equals y, but we don't know what z is equal to. Okay. We could get z in terms of x and y if we really wanted to. Or we could just solve for z directly, which is the easier way to do it with respect to the constraint. We have 2xz plus 2yz plus xy equals 12, right? Wasn't that was our surface area, right? Okay. And so what can I do? I can say that x is equal to y. So every time I see a y, I can put in, I can put an x or vice versa. Okay, so let's say this is 2xz plus 2xz plus x squared is equal to 12. Okay, so that eliminates z. What I'd like to do is I'd like to get z in terms of x if I can. Okay, so how could I get z in terms of x? Well, let's go to these two equations here. Okay, so if this is x, then we know that x times x, if x is equal to y, then that's x squared plus 2xz is equal to 2xz plus 2xz. That's interesting. Okay. Okay, so we could cancel this out. We could get x times x is equal to 2x times z. Okay, so what does this mean? Well, divide by x, and we say that x is equal to 2z. Okay, or z, we could say z is equal to x over 2. Okay, so x is equal to 2z, or z is equal to x over 2. Oh, okay. So now I can plug that in for z. Sorry, plug this in for z. Well, I've got 4 of these, right? So this is just 4xz plus x squared equals 12. Okay. Okay, and so yeah, so let's plug this in. This is 4x times x over 2 plus x squared equals 12. Okay. So what is this? This is 2x squared plus x squared equals 12. Interesting. Okay. So we've got what is this? This is 3x squared equals 12. Divide by 3, x squared equals 4. So x equals 2, right? It could be plus or minus 2. But this is a box. So I'm going to go with x equals 2. Oh, okay, cool. So if we know that x equals 2, then what does y equal? Yeah, y was equal to 1. Or sorry, y was equal to 2. Because x was equal to y, right? X was equal to y. Okay, and then if x and y are both 2, then what's z? Z is going to be 1, right? It's going to be 1 because isn't z x over 2?
A little bit, please.
Okay. So we know what the dimensions of this box have to be to get a maximum volume. Okay, so the max volume, okay, the max volume is equal to x times y times z, which is 2 times 2 times 1, which is 4 cubic meters, because this is in meters. Okay, the max volume is 4 cubic meters, and that occurs when x is equal to x is equal to 2 meters, y is equal to, well, I could just say the dimensions. When the dimensions are 2 meters by 2 meters by 1 meter. Okay, max volume and dimensions. Make sense? It's good.
Could you go over real quick how you went from the 2xz plus 2yz plus x squared equals 12 to the next line to the 4xz? I know we substituted with z equals and x equals, but I'm a little bit confused.
Oh, yeah. It's because when I substitute x for y, right, it goes in here, right? And then all I did was combine like terms.
Oh, okay. I forgot about the y part. I was focused on the z, but that makes sense. Thank you.
That's a little blurry. That's kind of weird. Okay, any other questions on this? Okay, I'm going to stop things there. We have an exam. This ends chapter 14. We have an exam on Wednesday of next week. Make sure you try the study guide. I'll be going over questions on the study guide on Monday. Okay? Okay, see you guys later.
Bye. Thank you.
Thank you.